Welcome to the fascinating world of chemical kinetics. In this video, we'll explore how and why chemical reactions happen at different speeds. Chemical kinetics is the branch of chemistry that studies the rates of chemical processes and the factors that affect them. Whether you're mixing baking soda and vinegar or watching rust form on iron, kinetics helps us understand the speed and mechanism behind these changes. Let's dive in and see what controls the pace of reactions and why it matters in everyday life and industry. Get ready to uncover the secrets behind reaction rates and how chemists use this knowledge to innovate. At the heart of chemical kinetics lies the concept of reaction rate. Simply put, the reaction rate tells us how quickly reactants are converted into products in a chemical reaction. This can be measured by tracking the change in concentration of a reactant or product over time. For example, if you observe a color change or the formation of bubbles, you're witnessing a reaction in action. Understanding reaction rates is crucial for controlling processes in laboratories, factories, and even in our own bodies. Let's see how scientists measure and interpret these rates. Not all reactions proceed at the same speed. Several factors can influence how fast a reaction takes place. These include temperature, concentration of reactants, surface area, presence of catalysts, and the nature of the reactants themselves. For instance, increasing the temperature usually speeds up reactions, while a catalyst can lower the energy barrier, making reactions happen faster. By understanding and manipulating these factors, chemists can optimize reactions for desired outcomes, whether it's speeding up a manufacturing process or slowing down food spoilage. Temperature is one of the most significant factors affecting reaction rates. When you heat up a reaction mixture, the particles move faster and collide more often, increasing the chances of successful collisions that lead to products. This is why reactions generally proceed more quickly at higher temperatures. However, too much heat can sometimes cause unwanted side reactions or degrade sensitive materials. Understanding the balance is key in both laboratory and industrial settings. Concentration of reactants also plays a crucial role in determining reaction rates. When there are more reactant particles in a given volume, collisions happen more frequently, which can lead to a faster reaction. This principle is used in many industrial processes to maximize efficiency. However, there's a limit. After a certain point, increasing concentration further may not significantly speed up the reaction. Understanding this relationship helps chemists design better experiments and processes. Surface area is another important factor, especially for reactions involving solids. When a solid reactant is broken into smaller pieces, its surface area increases, allowing more particles to interact at once. This is why powdered substances often react faster than larger chunks. In real life, this principle is used in everything from dissolving sugar in tea to designing catalysts for industrial processes. Maximizing surface area can be a simple yet effective way to speed up reactions. Catalysts are substances that speed up chemical reactions without being consumed in the process. They work by lowering the activation energy required for a reaction to occur, making it easier for reactants to transform into products. Catalysts are vital in many industrial and biological processes. For example, enzymes are natural catalysts in our bodies that help digest food and carry out essential life functions. Understanding how catalysts work allows chemists to design more efficient and sustainable processes. Chemical nature of the reactants themselves can greatly influence reaction rates. Some substances react quickly due to their molecular structure, while others are more stable and react slowly. For example, sodium reacts explosively with water, while gold is famously unreactive. By understanding the properties of different chemicals, scientists can predict and control how fast reactions will occur, which is crucial in both research and industry. Collision theory is a fundamental concept in chemical kinetics. It states that for a reaction to occur, reactant particles must collide with enough energy and the correct orientation. Not every collision leads to a reaction, only those that meet these criteria. This theory helps explain why increasing temperature or concentration can speed up reactions, as both lead to more frequent and energetic collisions. Activation energy is the minimum amount of energy that reactant particles need to successfully collide and form products. Think of it as a hurdle that must be overcome for a reaction to proceed. Some reactions have low activation energies and happen easily, while others require more energy input. Catalysts help by lowering this barrier, making reactions faster and more efficient. Understanding activation energy is key to controlling reaction rate. Rate laws are mathematical expressions that relate the rate of a reaction to the concentration of its reactants. They help chemists predict how changing conditions will affect reaction speed. For example, a simple rate law might state that doubling the concentration of a reactant doubles the reaction rate. Understanding rate laws is essential for designing experiments and scaling up reactions for industrial use. Order of a reaction tells us how the rate depends on the concentration of reactants. For example, in a first-order reaction, the rate is directly proportional to the concentration of one reactant. In a second-order reaction, it might depend on the concentrations of two reactants or the square of one. Determining the order of a reaction helps chemists understand the underlying mechanism and predict how changes will affect the rate. Reactions can be classified by their order, 0 first or second. In zero-order reactions, the rate is independent of reactant concentration. In first order, it depends linearly on one reactant. In second order, it depends on two reactants or the square of one. Each type has unique characteristics and mathematical descriptions. Understanding these distinctions is crucial for analyzing experimental data and predicting reaction behavior. Find the order of a reaction. Chemists conduct experiments and analyze how the rate changes with varying concentrations. By plotting data and using mathematical techniques, they can identify whether a reaction is 0 first or second order. This information is vital for understanding the reaction mechanism and for scaling up processes in industry. Accurate determination ensures efficient and safe chemical production. Degraded rate laws provide equations that describe how reactant concentrations change over time. These equations differ for zero, first, and second-order reactions. By using integrated rate laws, chemists can predict how long a reaction will take to reach a certain point, which is essential for planning experiments and industrial processes. Mastering these equations is a key skill in chemical kinetics. Half-life is the time required for half of a reactant to be consumed in a reaction. It's a useful concept, especially for first-order reactions, where the half-life remains constant regardless of concentration. This idea is widely used in fields like pharmacology, nuclear chemistry, and environmental science to predict how long substances will last or decay. Understanding half-life helps in planning and safety assessment. Graphical methods are powerful tools in chemical kinetics. By plotting concentration versus time or using logarithmic plots, chemists can determine reaction order and rate constants. These visual techniques make it easier to interpret data and spot trends. Graphs are essential for communicating results and making informed decisions in both research and industry. Arrhenius equation links reaction rate to temperature and activation energy. It shows that even small increases in temperature can lead to significant increases in reaction rate. This equation is a cornerstone of chemical kinetics, helping chemists predict how reactions will behave under different conditions. Understanding the Arrhenius equation is essential for controlling and optimizing chemical processes. Activation energy and temperature are closely linked in determining reaction rates. As temperature increases, more particles have enough energy to overcome the activation barrier, leading to faster reactions. This relationship is quantitatively described by the Arrhenius equation. By controlling temperature, chemists can fine-tune reaction speeds for optimal results. Catalysts play a vital role in industrial chemistry. They enable reactions to proceed at lower temperatures and pressures, saving energy and reducing costs. From refining petroleum to manufacturing fertilizers, catalysts are at the heart of many large-scale processes. Their use leads to more sustainable and efficient production, benefiting both the economy and the environment. Enzymes are biological catalysts that speed up reactions in living organisms. They are highly specific, often working on just one type of molecule. Enzymes are essential for processes like digestion, energy production, and DNA replication. By studying enzymes, scientists gain insights into both health and disease and develop new medicines and therapies. Reaction mechanism is a step-by-step sequence of elementary reactions by which overall chemical change occurs. Understanding mechanisms helps chemists explain why reactions happen the way they do and how to control them. Mechanisms can involve intermediates, catalysts, and multiple steps, each with its own rate. Deciphering these pathways is a key challenge in chemical research. Elementary steps are the individual stages in a reaction mechanism. Each step involves a small number of molecules and has its own rate. By analyzing these steps, chemists can identify which one is the slowest, known as the rate-determining step. This knowledge is crucial for designing better catalysts and optimizing reactions. Rate-determining step is the slowest step in a reaction mechanism. It acts as a bottleneck, limiting the overall reaction rate. By identifying and understanding this step, chemists can develop strategies to speed up the entire process, such as using catalysts or changing reaction conditions. This concept is central to both research and industrial chemistry. Intermediates are species that form temporarily during a reaction mechanism but do not appear in the overall equation. They are often unstable and react quickly to form the final products. Detecting and studying intermediates helps chemists unravel complex reaction pathways and design more efficient processes. Molecularity refers to the number of molecules involved in an elementary step. It can be unimolecular, bimolecular, or termolecular depending on whether 1, 2, or 3 molecules collide. Molecularity helps classify reactions and predict their behavior. Most reactions are unimolecular or bimolecular, as termolecular collisions are rare. Chain reactions involve a series of steps where reactive intermediates generate more intermediates, propagating the reaction. These reactions are common in processes like combustion and polymerization. Understanding chain reactions is important for safety and efficiency in both industrial and natural settings. Energy profile diagrams show the energy changes during a reaction. They illustrate the activation energy, intermediates, and the overall energy difference between reactants and products. These diagrams help visualize how catalysts lower activation energy and how energy is absorbed or released. Energy profiles are essential for understanding reaction dynamics. Reactions can be exothermic, releasing energy, or endothermic, absorbing energy. Exothermic reactions feel warm like combustion, while endothermic reactions feel cool like dissolving salt in water. Understanding these energy changes is important for safety, efficiency, and designing chemical processes. Kinetics and thermodynamics are two key aspects of chemistry. Kinetics tells us how fast a reaction occurs, while thermodynamics tells us whether a reaction is possible and how much energy is involved. A reaction can be thermodynamically favorable but still proceed slowly if the activation energy is high. Both perspectives are needed for a complete understanding of chemical processes. Chemical kinetics has countless practical applications. It's used in developing new medicines, designing industrial processes, preserving food, and even understanding environmental changes. By controlling reaction rates, scientists and engineers can create safer, more efficient, and more sustainable products and technologies. Kinetics plays a role in understanding and addressing environmental issues. For example, the rates of reactions in the atmosphere affect air quality and climate change. By studying these processes, scientists can develop strategies to reduce pollution and mitigate environmental damage. In the pharmaceutical industry, kinetics is crucial for drug development and delivery. Understanding how quickly a drug reacts or breaks down in the body helps determine dosage and effectiveness. Kinetics also guides the design of controlled-release medications and ensures safety and efficacy. Kinetics is important in food chemistry from cooking to preservation. The rates of reactions determine how quickly food spoils, browns, or cooks. By controlling temperature, pH, and other factors, food scientists can extend shelf life and improve quality. Kinetics helps make our food safer and tastier. Combustion is a rapid chemical reaction that releases energy, usually as heat and light. Understanding the kinetics of combustion is essential for designing engines, power plants, and safety systems. By controlling reaction rates, engineers can maximize efficiency and minimize pollution. Polymerization is the process of forming large molecules from small units. The kinetics of polymerization determines the properties of plastics, rubbers, and fibers. By controlling reaction rates, manufacturers can produce materials with specific characteristics for countless applications. Photochemical reactions are driven by light energy. These reactions are important in processes like photosynthesis, photography, and the formation of ozone in the atmosphere. Kinetics helps explain how light intensity and wavelength affect reaction rates, leading to innovations in energy and environmental technology. Electrochemical reactions involve the transfer of electrons and are central to batteries, fuel cells, and corrosion. Understanding the kinetics of these reactions helps improve energy storage, develop new technologies, and prevent material degradation. Electrochemical kinetics is a rapidly growing field with wide-ranging applications. Industrial catalysis is the use of catalysts to speed up large-scale chemical reactions. It's essential for producing fuels, chemicals, and materials efficiently. Advances in catalysis have led to greener processes, reduced waste, and lower energy consumption, making modern industry more sustainable. Chemical kinetics isn't just for scientists, it affects our daily lives. From how fast food cooks to how medicines work, reaction rates shape our experiences. Even simple activities like cleaning or preserving food rely on controlling chemical reactions. Understanding kinetics helps us make better choices and improve our quality of life. Studying chemical kinetics requires precise experimental techniques. These include measuring concentrations, monitoring temperature, and using instruments like spectrophotometers. Accurate data collection and analysis are essential for understanding and controlling reaction rates. Advances in technology continue to improve our ability to study kinetics. Data analysis is a critical part of chemical kinetics. By interpreting experimental results, chemists can determine reaction rates, mechanisms, and rate laws. Statistical methods and computer modeling help make sense of complex data, leading to new discoveries and innovations. Despite advances, chemical kinetics still faces challenges. Complex reactions, unstable intermediates, and extreme conditions can make experiments difficult. Ongoing research aims to develop better methods for studying and controlling reaction rates, opening new possibilities in science and technology. Future of chemical kinetics is bright. New technologies such as artificial intelligence and advanced sensors are revolutionizing how we study and control reactions. These innovations promise faster discoveries, greener processes, and new materials that will shape our world. Chemical kinetics will continue to be a driving force in science and industry. Summary: chemical kinetics is the study of reaction rates and the factors that influence them. From temperature and concentration to catalysts and mechanisms, kinetics provides the tools to understand and control chemical change. Its applications span medicine, industry, environment, and daily life. By mastering kinetics, we unlock new possibilities for innovation and problem solving. Thank you for joining this journey through the theory of chemical kinetics.